Okay, so welcome back. This is section 1.3, part 2. In this session, we're going to start off by taking a look at domains and ranges of functions. All right, so there are two ways that domains and ranges, but specifically domains of a function, can be described. That is explicitly or implicitly. Okay. If there is no stated domain with a function, then we go with this as an implicitly defined domain, where the implicit domain is the set of real numbers for which the equation is defined. So if it doesn't tell you, here's the domain, you look at the function and go, well, it's implied then that this thing is going to work for all the numbers that it works for. Whereas if something is explicitly defined, it will be a given domain along with the function. And it's probably easier to understand with an example. This example right here is an explicitly defined domain because we have a function and we have a restriction upon the domain from 4 to 7 inclusive. Now there's no mathematical reason why numbers larger than 7 or smaller than 4 wouldn't work. But for whatever reason, this function is only defined on that range of values. So we would say that this is explicitly defined, and it has a domain of set of all x's such that x is somewhere between 4 and 7. Now, if I just am handed this, we would say that, well, since it doesn't say what the domain is, then the domain can be any number for x, any real number for x that works. Now, obviously, we're going to have some issues with a 0 in the denominator at positive and negative 3, because either those squared minus 9 would give us 0 downstairs. So we would say that this has an implied domain of all x's that are not equal to 3 or negative 3. Okay? The set of all x's such that x is not equal to positive 3 or negative 3. Okay? So our first example down here asks us to find the implied domain and then the range that is associated with that. So the first one over here I have on the left is f of x equals the square root of x plus 5. Well, there is no stated domain, so I'm looking for the implied domain. And here's what I remember. I remember that you cannot take the square root of a negative number, which implies to me then that this radicand, and radicand is the fancy name for the stuff under the root, can't be negative. So to find this implied domain, I'm just going to make that happen. I'm going to say, what makes my radicand greater than or equal to 0? And then with a little bit of manipulation, I can say that this is when x is greater than or equal to negative 5. So then the implied domain is going to be the set of all x's such that x is greater than or equal to negative 5. It also asked me to find the range of this thing. So what is the range of this thing? Well, I remember from my algebra that the plain old square root function looked like that, right? That was just y equals square root x. And so how is this one related to that one? Now, something we have not yet talked about, but you should remember from algebra, is the transformations. And this has had a horizontal transformation. It's been shifted 5 units to the left. So it's over here like this. This would be negative 5, and you can see that transformation right there in the domain. And so basically it looks like this thing is going to have a range, the set of all y's, such that y is greater than or equal to 0. Okay. Now, if you can't just look at it and know that, could you have graphed it and seen how it looked? And would that be an appropriate way to find that domain? Okay. All right. Second question, same stem, find the implied domain and range for the function. Here's my function. It looks like I'm looking at a more complicated problem because not only do I have a root, but I have a root in the denominator. So while a moment ago we said that the radicand couldn't be negative, now my radicand can't be negative because of the root, but it also can't be 0 because I'm not allowed to have a 0 in the denominator. So how do I make that happen? I literally just say, when is this greater than 0? And it will be greater than 0 when x is greater than 4. So then my domain will be the set of all x's such that x is greater than 4. And then what will my range be? Now, I don't think that this one's going to look like that picture anymore because it's not just a root, it's a root downstairs. So I'm not certain. So what I'm going to do is I'm going to take a look at the graph. So I'm going to go to my favorite graphing tool, which is Desmos. And I'm going to take a look at the graph of this thing. Yeah, just take me there. So this was y equals 1 divided by the square root of x. Was it minus 4? I believe it was. And it looks like, if I zoom out, yeah, there's no piece over here in this third quadrant. There's nothing down here in the fourth quadrant. There's nothing over here in the, what is that, second quadrant. Okay? So there's nothing over here. I wonder why this is, no, basic colors. Will this allow me to scribble? I don't think it will. Anyway, there's nothing down here in this second quadrant, third quadrant, or fourth quadrant. It's only over here in the first quadrant. And it looks like, if I zoom in on it, it looks like it has one of those horizontal asymptoty things where it's getting closer and closer to 0 as we go out and out and out and out and out. So I'm guessing it looks like my range should be the set of all y's such that y is greater than 0. Sounds good to me. So in the first example, I was able to figure it out kind of logically using some information I know about roots. But in the second one, no idea what that looks like, so I'll graph it and take a look at the picture. Okay, special types of functions. A function from x to y is said to be a one-to-one. That's the special type of function. A one-to-one function when each y value in the range corresponds to one exactly one x value in the domain. So what does this mean? Well, let me give you an example. Let's say that we were looking at this guy, y equals x cubed. This is a one-to-one function because if I pick any x value, there's going to be only one y value that corresponds to it. Or if I pick any y value, there's only going to be one x value. So if I call this x1 and y1, then this would be y2, and there would be a x2 over there. So what we're looking at is, we're looking at a function where every x gets one y, and every y gets one x. Now correspond that to our good friend the parabola, y equals x squared. Okay. For this, if you pick a y value, there is potentially going to be two x values that give you the same y value, which makes that not one-to-one. The reason that we like these better than these, or the reason that we classify them as one-to-one, is the one-to-one functions, these have inverses. Meaning if I can start at x and get to y, I can start at y and get back to x. These don't. Because I can start at this x, end up at y, and then go from that y and end up back here at this x, which wouldn't be back where I started. And I don't like things I can't undo. We like to be able to do something and then undo it. Okay? Some more special type of functions. A function from x to y is called an onto function when it uses all of y. Here's a super, super simple example of what that means. Here's the function y equals x. It is an onto function because every value in y is in the domain. Every value in big Y, I should say. Remember, big Y is the set of all real numbers. So every X gets used, every value in X gets used, and every value in Y gets used. This one over here is also onto, by the way. This one is not onto because you're missing all the negative Y's. Okay? All right. Speaking of graphs of functions, what is the graph of a function? I keep saying it, but what really is it mathematically? Well, the graph of a function consists of all the points x comma f of x, where x is in the domain of f. The graph of a function, y equals f of x, consists of all the points x comma f of x, where x is in the domain of f. So basically what we're doing is we're making a bunch of ordered pairs. We're plotting all those ordered pairs. How many of them? All of them. Okay? You can tell if something is a function or is not a function based on the vertical line test. The vertical line test says that if you pass a vertical line over your graph, if it only intersects at one point, then you have a function. Or it could intersect at no points too. That would work too. It can't intersect at more than one. Okay? So, for example, is that a function? And the answer would be no, because there are two intersection points. And what that tells me is, and if we go back to the definition from a long, long time ago, like the last video, that there is one x value over here. I don't know what it is, but that x value has two y values. And that violates the definition of a function, because the definition of a function said that 1x had only one y, and this one has two y's. So that is not a function. Is this a function? Most certainly is, because that vertical line is only going to pass at one point. So that is a function. Is this a function? It most certainly is, because a vertical line will only ever intersect at most once. The fact that there's a chunk here missing, nobody cares. That just means that there are values in the set x that are not in the domain of the function. There are numbers that don't work. For whatever reason, it looks like between 0 and 2, not including 0 and 2 because those solid dots on there aren't in there. Now, one thing you should keep in mind, and this is something that bothers the heck out of me, but I have yet to find any online graphing tool, anything out there, that will actually do this and put these little arrowheads on the end. So when you see graphs like this, we should assume that this is meant to go on forever. If I didn't want it to go on forever, I would either do a solid dot on the end or a hollow dot on the end, meaning that the endpoint is either included or not included, respectively. Okay, so when you read a graph, assume that it goes on forever. Okay? All right, some graphs you should know. Obviously, the identity function f of x equals x, or y equals x. The line y equals x, f of x equals x, identity function. The parabola, the cubic. These are graphs that you should just look at them and go, yeah, I know that one. Yeah, I know that one. Yeah, I know that one. The root function, the absolute value, the rational function 1 over x. These are ones that are basic functions that we use again and again and again and again. And then what we do with them is we do transformations of these graphs and create families that have the same basic shape. Now, we talked about this a moment ago when we talked about our root of x plus 5. But a transformation of a function is where we take a function, take that basic shape, the y equals x squared, our squaring function, and we say, hey, let's move this thing around. Can we move it up? Can we move it down? Can we move it left? Can we move it right? Okay, but up and down and left and right aren't good terms. We want to talk about a vertical shift and a horizontal shift. Vertical shifts are achieved by adding or subtracting a constant value to the function. Okay? So by adding or subtracting a number. Adding a number shifts you vertically up, positive vertical shift. Subtracting a number shifts you vertically down, a negative vertical shift. Horizontal shifts are achieved by adding a constant value directly to the variable, So the x that was squared is now x plus 2 that is squared. And remember that x is a liar. So adding a constant value will result in a horizontal shift left. So adding 2 shifts that vertex over to negative 2. And then subtracting would move it right, be a horizontal shift to the right. Okay. We can also do reflections. And then if we want, we can do combinations of things where we do shifts and reflections. And it looks like in that last example over there, this thing has been moved a couple of times. There's a vertical shift, there's a horizontal shift, and there is a reflection. Okay? Remember that transformations occur according to the order of operations. So if you were to evaluate this function, the first thing that you would do is you'd add that 3. That means that the horizontal shift happens first. The next thing that you would do in terms of transformations, obviously the squaring is the next thing, but the next thing in terms of transformations is that negative, which means you would flip it upside down. And then the last thing that you would do is you'd add that 1, which is that vertical shift. Okay? The order in which you do these matters. Because if you don't perform your transformations in the correct order, you would not get this same graph. If you shifted up before you flipped, whoa, why do I have so many arrows? If you had shifted up before you flipped, okay? So if you slid it left and then went up and then flipped, you'd end up down there. And that's not the right graph. So make sure that when you're performing transformations, that transformations always are applied according to the order of operations. Okay? So here is the synopsis of transformations. This is what you should know about transformations. Transformations are horizontals, verticals, and reflections. All right, we have 2 examples here for transformations we're going to do, and then we're going to end this video. This one's actually going to be a 3-part section. Okay? So my job here is to describe the transformations and then graph those transformations. Okay? So first things first, over here on the left. All right, so what was the parent function? Where did this thing come from? Ooh, I see it. See the squared right there? That means this was originally our squaring function, our parabola. And what's happened to it? Well, this has happened to it, that's happened to it, that's happened to it, and that's happened to it. So 4 things have happened to it. What does each of those 4 things do? Well, this is a horizontal shift. And why am I starting in there? Because Aunt Sally told me to. Please excuse my dear Aunt Sally, order of operations. So this is going to be right 4 units. And then what? Oh, the 2 and the negative. So 2 is a vertical stretch, and the negative is a flip. So we have a vertical flip and a stretch. And then what does the 5 do, the last thing? Oh, that's going to shift it up. Okay? So if I were to make a sketch of this thing, okay, I'm going to start out with what the parent function was. So the original function was that guy. And then it moved right 4 units. And then it was stretched and flipped. And then it was shifted up 5. And so my final graph would be something like this. Now, I don't expect you to be able to graph these things perfectly, but you should be able to walk through what we just did right there. Where did it start? What happened to it? And where does it end up? Of course, if you're uncertain as to the accuracy of this, you can always just go over here and graph the thing and see what it looks like. So we have y equals negative 2 times the quantity x. Was it plus 4 or minus 4? Y equals negative 2 times the quantity x minus 4, and then plus 5. Oop, I forgot my squared. There we go. Now the question is, does that look like what I drew? And then if I change my scale, I can make it look exactly like what I drew. But yeah, looks pretty much like what I drew. Okay. So can we do the same thing over here? What's the original function? Square root of x. What's happened to it? That, and that all happened to it. Okay. What's the negative 4 do? Right 4. What's the 3 do? Stretch vertically. And what's the 5 do? Up 5. So what was the original function? And the original function was square root function. And then it went right 4. And then it was stretched vertically by a factor of 3. And then it was shifted up 5. And so in the end, it looks something like that. Right? So what you should be able to do is you should be able to look at a function and say, okay, where did this start? What has happened to it? And be able to then say, oh, okay, I know what this graph should look like. Right? That's 20 minutes. I'm going to end the video here and come back with classifications and categories of functions, and that will be part 3.